Chapter 4 deals with triangles. In particular, it deals with relationships between two triangles. So when we talk about congruent triangles, what do we mean? Triangles that are congruent have the exact same sides and the exact same angles as each other. And we'll get into an example in just a second. So we have this very important acronym. We call it corresponding parts of congruent triangles are congruent. So let's break this down a little bit. We've got parts of triangles. So we're talking about two separate triangles. Let's give you an example here. So let's say we have these two triangles, triangle NBC and triangle FOX. If we know that these two triangles are congruent, then all of the parts are congruent as well. So for example, side length NB is congruent to side length FO. BC is congruent to OX. NC is congruent to FX. So all the sides are congruent. Also, the angles are all congruent. So for example, angle N has to be congruent to angle F. Angle B has to be congruent to angle O. And angle X and angle C are also congruent. So that's what we mean when we talk about corresponding parts. Corresponding basically means parts that are in the same spot. So if I talk about angle N, I see angle N and angle F are both kind of in the first position of the names. So that means angle N and angle F have to be corresponding congruent parts. So that's the CPCTC. CPCTC, you can say it really fast if you want to. Corresponding parts of congruent triangles are congruent. So it just so happens that the CPCTC is a biconditional. So if we have congruent triangles, then corresponding parts are congruent. Likewise, if corresponding parts are congruent, then the triangles themselves are congruent. So that's going to be a helpful tool when we use this statement to prove triangles are congruent or prove certain parts of triangles are congruent. So the CPCTC, it's a helpful thing. Make sure it's in your notes. Here's a brief example. Let's say we know that triangle ABC is congruent to triangle XYZ. Well, XYZ is over here. It's not labeled, so we'll have to go and label it. I see angle A. A is kind of in the corner here, this right angle looking like corner. And since A comes first in the name ABC, and X also comes first, that means X is the corresponding angle to angle A. Likewise, Y and B are corresponding because I see B and Y sort of share the same space. Now B, I see B is kind of attached to this short leg and this long hypotenuse. So that means angle Y also has to be attached to the short leg and the long hypotenuse. So there's angle Y. And then lastly, C is kind of at the pointy end of this triangle, so that means Z for the corresponding side has to also be in that pointy side. So according to the CPCTC, we know a ton of different things are congruent. All of the angles are congruent. So we can go through and start labeling. I know angle A must be congruent to angle, well, A follows X, so angle X. So we know all three pairs of these corresponding angles are congruent, right? Angle A is congruent to angle X, B is corresponding and congruent to angle Y, and Z and C are congruent as well. So that deals with the angles. Also the sides are congruent. And AC congruent to XZ. So that means this side length is congruent to that side length. The hypotenuse is congruent to the other hypotenuse. And that long leg is congruent to that long leg. One last example here. Let's pretend like we have triangle CAT and we know it's congruent to triangle DOG. Without drawing any pictures of triangles, we can figure out the completions of these sentences. So segment TA, well, TA refers to those two sides. TA would be congruent to segment GO because it follows the same order in the name, T to A, G to O. Angle C, well, angle C is that first angle, and it corresponds with the first angle in DOG. So angle C is congruent to angle D. And then finally, segment DG. Well, DG is like first, last in the name DOG. So first and last, first and last. So segment CT would be the segment that's congruent to segment DG. Here I have two triangles. They kind of share a side, and I need to identify the congruent triangles by their names. So I've got a triangle on top, a triangle on bottom. It doesn't matter which one I start with, but I'll just start with the top one for fun. So I've got, let's say, triangle ABC. And to start off, it doesn't really matter what you name the very first one. I just happen to go in alphabetical order. Now, triangle ABC is congruent to which triangle? The order of the letters that you pick is very important. Here I started with ABC. Start at A, head toward B, end up at C. I'm going to follow the same steps to name the second triangle. In other words, I'm going to follow along this segment that has one congruence mark, and then I'm going to follow down this other segment with two congruence marks. So start at A, head towards C. So for the second triangle, I'm going to follow the same method, just down the other direction. Start at A, head toward D, end up at C. So that triangle is named ADC. Here's another example. We can start with the triangle on the left or the triangle on the right. Doesn't really matter which one you start with. I think I'll start with the one on the left. Let's say triangle PQS. And which one is that congruent to? So we start at P, and angle P, that angle is made up of a segment with two congruence marks and a segment with one congruence mark. So that tells me angle P is corresponding with angle R. So I know that the second triangle's name will start with R. Now, I go from P to Q, which follows along this segment with one tick mark. So that means I'll have to follow from R along the same segment. So PQS and RQS. S. Take a minute and try this next example on your own. Here's one possibility. MNO is congruent to QPO. There are other possibilities as well. That's another possibility. Can you think of another possibility? Let's take a look at another example. Lastly, so we've got this triangle down below here. Let me just shift up a little bit. We're dealing with triangle RTV, let's say. So what are we going to name our second triangle? If we start at R, that angle is made up of a congruence segment 2 and 3. And so I need to start at angle U. The reason is it's also made up of a segment with 2 and 3 congruence marks. So R corresponds with U. Now, we moved from R to T to V. So R towards T, head up at V. Again, we're going to start at U. We're going to move along that parallel line and end up at V. So it should be U, S, V. And those are those congruent triangles. So we can use the CP-CTC to prove that triangles are congruent, right? So all we would have to do is show that all pairs of corresponding parts are congruent, and then we could say the triangles are congruent. Well, the problem with that is we'd have to establish 6 different things before we could prove that the triangles are congruent. Not only would we need to prove that all 3 pairs of sides are congruent, but we'd also have to prove that all 3 pairs of angles are congruent as well, which is tedious. That's a whole lot of work. Well, the nice thing is we don't need to have all 6 things. In fact, we've got a couple of theorems that allow us to cut that number in half. So I'll give you a couple of examples in order to prove that triangles are congruent. One of the theorems that we have to prove that triangles are congruent is called the SSS theorem. Oh, just a sec here. And what that means is, if we can prove that these segments are congruent, that these segments are congruent, and that these segments are congruent. If we can prove that those three pairs of segments are congruent, then we can guarantee that those two triangles themselves are congruent. So that's called SSS, or side, side, side. Another theorem we have to prove that triangles are congruent is called the SAS theorem. Now, SAS stands for side, angle, side. And so what that means is we need two pairs of sides. Let's say these sides were congruent and these sides were congruent. And then we need an angle to be congruent as well. However, that angle must be the included angle. And what that means is the angle that we know something about must touch the two sides that we know about. So if we know that these two angles were congruent, then we could prove that the triangles themselves are congruent. However, if instead of those two angles, if let's say we knew that these two angles were congruent, that is not enough to say that the triangles themselves are congruent, because that's not the included angle. So by included, I mean it has to touch the two sides that we know something about. Let me show you another example. If instead of these two sides, what if instead of those sides we knew that, let's say, that side, those pairs of sides were congruent, and these sides were congruent? Well, we could still use side, angle, side if we knew that these angles were congruent. Because again, they're the included angles. They're in between, or so they sort of follow the sides that we know something about. So that's side, angle, side. The next theorem we have is called ASA, or angle, side, angle. This theorem is similar to side, angle, side, except now we're using the angles as, well, I guess you could kind of think about it like a sandwich. Let's say that we knew that these angles were congruent. There we go. And let's say these angles were congruent. If the included side was also congruent, the included pairs of sides, if those were congruent, then we could prove that these two triangles are congruent. So again, that side must be the included side. So another quick example with this one. If we knew that these two pairs of sides were congruent and these segments were congruent, that would be enough to prove that the triangles themselves were congruent. And one final theorem that we'll deal with is called AAS. In other words, angle, angle, side. For this theorem, we want to make sure that the side we're talking about is not the included side. So an example of this, let's say we have these angles congruent, and we've established that these angles are congruent. Whoop. Now it's possible that if these sides were congruent, then we would follow angle, angle, side. And again, it's kind of like the order in which you see the things. Here's angle, angle, side, angle, angle, side. So we have those four theorems that we're dealing with. Side, 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 angle, side, angle, and angle, angle, side. Can you prove that these two triangles are congruent? First off, let's go through and name the two triangles. So is it possible for us to prove that ABD and CBD are congruent? Well, these tick marks right here show me that AB and CB are congruent. Also, I've got a right angle right in there. And if that's a right angle, well, this angle and that angle, they're both right angles because we've got some perpendicular lines. Well, perpendicular lines make right angles, and right angles are always congruent to each other. So that means angle ABD. So right now we have a pair of sides and a pair of angles. Then notice that this side length, BD, is a shared side. It's shared in both of the triangles. And so that means in triangle ABD and CBD, it's got to be the same in both of them. So yes, we can prove that these two triangles are congruent, and we can prove it because of side, angle, and then that shared side. So we can prove that these two triangles are congruent using the side-angle-side theorem. What about these? Can we prove that these two triangles are congruent? First off, let's name them. So we have triangle DEF and DGF. Well, let's figure this out. We've got a pair of sides that are congruent. That refers to these segments. So let's label those. We've also got a pair of angles that are congruent. There's those. Maybe I'll just number them angle 1 and angle 2. So now we have a pair of sides and a pair of angles. We also have, just like in that previous example, we've got this shared side up the middle, DF. So that means that, in both triangles, DF will be congruent to itself. So we've got a pair of sides, a pair of angles, and we've got that shared side. So it seems like this might follow side, angle, side. However, the angles, angle 1 and angle 2, are not included angles. And again, just a reminder of the definition of an included angle. The included angle must touch both sides that we know about or that we care about. In other words, angle 1, in order for us to use angle 1 as an included angle, did I say angle or side? In order for us to use angle 1 as an included angle, it would have to be created with this segment EF, but it's not, right? That red angle only is made up of this blue segment, the shared DF. And likewise, angle 2 doesn't touch segment GF. So these might be congruent, they might not be congruent. We can't prove that they're congruent. So if they're not provable. Let's try another example. What about these triangles? Let's name them first. So we've got DEF and GHF. So, what does it mean for two segments to bisect each other? Well, bisect means cut in half. And so each of these segments is cutting the other one in half. I know EH is bisecting DG. So that means EH is doing the cutting and DG is being cut. In other words, DG is cut into two equal parts. And then also, since they bisect each other, DG bisects EH. In other words, EH is cut right in half. So I have two pairs of congruent segments that come from this fact. And then one last thing, whenever we have lines that intersect, we create these vertical angles. So I could talk about angle DFE and angle HFG. Vertical angles are always congruent, and so that means that those two angles are congruent, so DFE. So we have two pairs of sides, the reds, the greens, and a pair of angles. So it's possible that we can use side, angle, side. The only thing that's left to check is, are these blue angles, are they the included angles? Well, how can we check? The way that we can check is the blue angle connected to both pairs of sides that we know about? In this case, they are. I see that blue angle touches both the red and the green, and as a result, that blue angle is made up of both of these sides that we know something about. So yes, indeed, these angles are indeed congruent, these triangles are indeed congruent, and they are congruent by SAS. How about these triangles? Can you prove that they're congruent? Well, I got one pair of sides. I got two pair of sides. And I got the shared side up the middle, US. And so that means, yes, indeed, I can prove that these triangles are congruent by side, side, side. So here we have congruent triangles. Let's try another. All right, are these two triangles congruent? So it looks like from the drawing we have that angle U and angle R are congruent. We know that T is the midpoint of RU, and RU refers to this segment from R to U, and so T is the midpoint, means that these segments are congruent in length. So we have a pair of angles, we have a pair of sides. We need one more pair of angles in order for these pairs of triangles to be congruent. We have intersecting lines, which means vertical angles are produced, and vertical angles are always congruent, and so that means we have angle, side, angle. And so therefore we can prove that these two triangles are indeed congruent by ASA. Let's try one more example. Can we prove that these two triangles are congruent? Well, let's figure out the given information. We've got a given pair of angles. Angle N and angle L are congruent. I got a pair of segments, pair of sides that are congruent, JK and MK. And the way that the triangles are drawn, we've got a pair of intersecting line segments. And whenever line segments or lines intersect, we make vertical angles, and vertical angles, of course, are congruent. So we have two pairs of angles and a pair of sides. We have a choice between angle, side, angle, or angle, angle, side. Which one do we pick? Well, the question is the side, is it included or not? And by included, I mean, is that side touching both of the angles? Well, JK is only connected to one pair of angles. It's kind of leaving angle N all by itself. Likewise, segment MK is connected to this middle angle, but it sort of leaves angle J by itself. So that means the sides are not included, but we can prove that the two triangles are congruent by angle, angle, side.